In this video, I'll draw the Lewis structure and get the molecular geometry and polarity for methane, CH4. I have other videos explaining covalent bonding, Lewis structures, and valence shell electron pair repulsion or vsepr theory, so I'll refer you to those videos. Methane is CH4. Generally, we'll write the molecular formula with the atoms as they appear on the periodic table left to right. Here we have hydrogen on the left, carbon on the right, so we would put hydrogen first. However, in cases like this, hydrogen will typically go second. Now, in general chemistry, we usually write hydrogen first only for acids. And so in these examples, you'll see hydrogen written second. So the first step to drawing the Lewis structure is to first count the total number of valence electrons. Right here, we have one carbon and we have 4 hydrogen. Here's the shortcut for valence electrons. If you look on the periodic table, you just go to the top of the family. So here's carbon. We'll look at that second number here in 14. That's 4, or family 4A. And for hydrogen, 1. So for one carbon, there are 4 valence electrons. Hydrogen has 1 valence electron, but there are 4 total hydrogens. So that's 4 total electrons. That gives us 8 valence electrons. Lewis structures are 2D visual descriptions of the way the valence electrons are bonding or non-bonding. So we want to draw the structure so that we can show the viewer all of the valence electrons. So the next step here is to put the least electronegative atom in the center. There is a rule here. Hydrogen can never be in the center. So in this case, carbon goes in the center, and anywhere around the carbon, we'll draw those 4 hydrogen atoms. Now, in general chemistry, we usually look at what are called small molecules, or what that means is molecules that have just one central atom. So hydrogen is the central atom. Anywhere around the central atom, we'll draw the other atoms. And I'm not worried about geometry or shape yet. We'll get to this part in just a little bit. So once we have those atoms around the central atom, we'll draw a line to connect those atoms. And these lines actually represent a covalent bond, or one shared pair of electrons. And so the goal is to show all of these 8 valence electrons in our Lewis structure. We want to show the reader where those 8 valence electrons are. So by drawing this structure, I've drawn a pair of electrons right here. That's 2. Here's another 2, and this bond here is another 2. So total 8 valence electrons. So I'll subtract that from the total. And this is our end goal for Lewis structures. You want to see this 0 count for the valence electrons. This means that all the valence electrons are accounted for in the Lewis structure. So here's my Lewis structure for methane. And the Lewis structure again is in 2 dimensions, or 2D. Next, let's use vsepr theory to get a shape for methane. This is the table that I use in my class. Every chemistry book is going to have some version of this table. And so we read this table going from left to right. So let's start here. Let's count the number of groups around the central atom. Groups are lone pairs plus atoms. Around the central atom, I count 1, 2, 3, 4 atoms, and there are no lone pairs around the central atom. So we'll go to our table and we'll look for number 4, and there's a block here that has 4. And this will give us the electron pair geometry. All this means is this is the geometry of the electron pairs. Now, in this case, we have for bonding pairs, we have 0 non-bonding pairs or lone pairs. So the shape here for those 4 electron pairs, tetrahedral. 4 groups around the central atom, and that gives us an electron pair geometry of tetrahedral. The molecular geometry is dependent on how many bonds or lone pairs are present. So in this case, we have methane with 4 bonds and 0 lone pairs. So we're looking at this line right here. And notice that's going to give us our specific name for the molecular shape or molecular geometry. So that's also called tetrahedral. 4 bonds and 0 lone pairs around the central atom. That gives us a shape of tetrahedral. That's important because tetrahedral means 4 faces, so it looks like a pyramid. So the optimum bond angle is 109.5 degrees. I want you to pause and just think about that for a second because look at the way I drew it in 2 dimensions. These bond angles right here look as if though they're 90 degrees. Now in 2 dimensions, that's okay to sketch the Lewis structure, but the actual shape is tetrahedral, so those bond angles are 109.5. And in my class, I always add the hybridization here. In my general chemistry class, I'll introduce hybridization. In my organic chemistry class, we'll go into a little bit more detail on the hybridization. But just to sum up for my Gen Chem students, when you're looking at hybridization, you're really connecting it with this number right here. So how many groups or pairs of electrons are around the central atom? Those 4 groups or 4 pairs of electrons have to be housed in hybrid orbitals. And so you see here we have sp3. So these are 4 hybrid orbitals, 1 from the s, 3 from the p, that mix to give us these special orbitals for bonding. I also have another lecture on hybridization where I explain this in more detail, so you can check that video out. So the carbon atom is sp3. Now, before we get to the polarity, let's look at the actual ball and stick model. Let's take a look at this tetrahedral. So I'm going to use the ball and stick model. Most of your chemistry kits will have a carbon, usually with a black atom like this. There's 4 holes in there. So I'll go ahead and stick these bonds in here. And you can start to see what that tetrahedral is going to look like. We are dealing with hydrogen atoms that are bonded to the carbon. Hydrogens are white atoms. So there's a white atom right here. It may be hard to see. So I'm just going to change the colors. Again, these are all hydrogens, but I just want to show you different colors to stand out against this white background. And there you go. There's your tetrahedral. So a lot different than what you're looking at right here. So in 2 dimensions, it looks like these bond angles are 90 degrees, but when you actually look at the shape, you can actually see there's bonds coming towards you, bonds going away from you. And so here's how we're going to sketch this. I'll go ahead and draw it like this. And so right here, we've got some bonds that are in the plane. So this is called the wedge and dash sketch. You can see this bond angle opens up a little bit. It's a lot more than 90, so this is 109.5. So that's this bond angle. And then on this side with this blue and the green atom, you can see when I hold it like this, the blue atom is actually pointing towards you, and the green atom is actually pointing away from you. So this is how we're going to sketch this. The atoms that are pointing towards you, we'll put those in wedges. And then the atoms that are pointing away from you, we'll put those in dashes. Now, if you look at this green atom, if I hold it this way, it's directly behind this blue atom. But when we sketch it, I'll go ahead and draw it just a little bit off-centered, just so that we can see it. And so these dashes represent atoms that are going away from you. You can almost see that pyramid shape, and this is what it looks like. To study polarity, we need to study the individual dipoles. In methane, we have carbon and hydrogen. So carbon farther to the right of the periodic table, slightly more electronegative than hydrogen, very, very small though, but it's still there. So this carbon atom is actually withdrawing some of the electron density from this bond here. And so that's going to make this bond slightly polar. So we're going to draw a dipole, very small one, going to carbon. And as you can imagine, we have the same, exact same dipoles from the other bonds. So while there are dipoles in the molecule, you can see that all those dipoles are going towards the center equally. And so right here, we can call this a symmetric molecule. And symmetric means non-polar. In other words, these dipoles are canceling each other out, so there is no net dipole moment for methane, and thus methane is a nonpolar molecule.